Hello guys, welcome to a new video. In this opportunity we want to solve this problem on which we have a pendulum with a point of support that is moving vertically according to the expression y equal h, where h is a function of the time, some given function of the time. The first step, define the Lagrangian, taking as generalized coordinate the angle that the pendulum makes with the vertical. And the second is to write down the Lagrange equation of motion, showing in particular that the pendulum behaves like a simple pendulum in a gravitational field. All right, so with this problem, what we are gonna do first is to write the Cartesian coordinates of the mass. For example, if we have the mass right here, right, the blue one, I just on the same illustration pointing on the mass, the coordinates are x and y. Okay, we have our origin right here, right? We want to know what is the Cartesian coordinates of this mass. This is our origin, but if we take this part, because we have the mass right here, so we have the mass right here, so we have this distance between the mass and the origin here as x, okay, and this distance, this distance as the y distance, okay. We can see here that this distance x, according to the geometry of the problem, this distance x is this one, and x is equal to, according to the geometry of the problem, let's see that we have here a right triangle, and this is the opposite side, so this would be L sine of theta. So that's easy, right? This is the adjacent side, the y side, the vertical side, and this is y, and this is the adjacent side, right? And this one is gonna be y equal. We need to take into account that we have all this distance. Let's see. We have all this distance, and all this distance is h. The red distance is h, and the blue distance is y. Is L cosine of theta, this blue distance, right? So y is h as a function of the time, because h changes with the time, minus L cosine of theta. Okay, so those are the Cartesian coordinates for the mass. Well, we can write down those Cartesian coordinates. And let's see, this is the part A of the problem. The Cartesian coordinates are x equal L sine of theta, and y equal h as a function of the time minus L cosine of theta. And we call these equations equation number 1 and equation number 2. Okay. Using the notation, okay, we have the notation that the velocity for a body that is moving with a specific velocity, we have the velocity is equal to, for example, if we have a velocity along the x coordinate, along the x-axis, this is going to be x dot, and this is going to be the derivative with respect to time of the coordinate, in this case x, and the same for y as well. So that means that we can write y, the velocity along the y-axis, as y dot equal to derivative with respect to time of y. Okay, so we use this notation. We are going to use the notation, the dotted notation, to write down the velocities. That way we can write the velocities as x dot. We want to find the velocity, so we have already the Cartesian coordinates. We want to write the velocities down, and this is going to be obviously the derivative with respect to the time of the coordinate. L is a constant. The L is going to be the length of the pendulum, right? As is shown in here, L, and this is constant. Okay, this is constant, so we can write this first like L. I am derivating equation number 1, L, derivative of sine of theta is with respect to time is going to be theta dot cosine of theta. Cosine of theta. I use the chain rule, right? And I will do a little explanation in a little bit. So let me write down the equation for y dot. Y dot is going to be something similar. H is a function of the time, so I have the derivative with respect to the time of h plus, okay, here is minus L. The derivative with respect to the time of cosine of theta is going to be theta dot, and the derivative of cosine is minus sine of theta. Then we have this equation as h dot plus L theta dot sine of theta. And I will call these equations number 3 and number 4. Okay, let's see something here real fast. Okay, I will highlight equation number 1, equation number 2, equation number 3, and equation number 4. Okay. What I did to find the equations number 3 and number 4, I used the chain rule. You remember the chain rule, right? The chain rule, if you have a function f, let's take the sine of theta, and theta is a function of the time. Then if you want to calculate the derivative with respect to the time of sine of theta, you have to do something like this. You have to take the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Okay? So is the derivative of the other function would be sine of theta. The other function is sine, right? So the derivative of sine is cosine evaluated at the inner function times the derivative of the inner function, in this case with respect to time, would be theta dot. So that's the chain rule, and we do that on equation number 1 and number 2 for the sine and cosine equations respectively, and we get equations number 3 and number 4. Okay, let's go now and let's go and write down the kinetic energy of this pendulum. Then the kinetic energy is equal to T equal to, as definition, we have that the kinetic energy is one mass, 1/2 of the mass times the velocity squared. But we have here that the velocity is the composition of the Cartesian components of the velocities. So we have x squared dot plus y squared dot. Okay? That's our velocity. That's the velocity of our pendulum. Okay? I will write it down here. Let's see, we have our velocity squared is components of the velocity, the composition of the components of the velocity. We have here this expression, and this is going to be 1/2 of the mass. Okay, let's write down the x component would be L theta dot cosine of theta squared plus h dot plus L theta dot sine of theta squared. That's our kinetic energy. Let's go and simplify this equation like this. So we do this, T is equal to 1/2 of the mass. Okay, let's do something. Let's do this part. This part is going to be L squared theta dot square cosine squared of theta plus, let's do this part right now. So we have the square of a binomial expression, and we remember that by the algebra, right? So we remember that, let's do a parenthesis here real fast. A plus b squared is equal to a squared plus b squared plus 2ab, right? The binomial theorem. Okay, so it's the same. So let's do h dot square plus the second term squared L theta dot sine of theta squared plus 2 times the first times the second term plus 2 times h dot L theta dot sine squared of theta. All right, let's keep going. Then we have the following. These two terms, we are going to get these two terms, this one and this one. and we are gonna put them together, and we are gonna go and take common factor L squared theta dot square, like this. These two terms, 1/2 of the mass. Okay, these and these are equal, right? I take common factor of them, and I have that term is common factor of cosine squared of theta plus sine squared of theta, plus this term h dot squared plus this term 2h dot L theta dot sine square of theta. As we all know, this term is equal to 1. This is a trigonometric property, right? Our kinetic energy is going to be finally written as. Finally, our kinetic energy is going to be something like this. 1/2 of the mass, L squared theta dot square plus 2h dot L theta dot sine of theta plus h dot square. This is our kinetic energy. We are going to call it equation number 5. Well, let's see here. We highlight our equation number 5, and we are ready to write the next equation. Okay, let's write down the potential energy, V. Okay, let's go to the illustration and see what the potential energy is. I will erase this. We have our coordinate y as h minus L cosine of theta, right? This distance is the distance that we are going to use to calculate our potential energy, and as we know, the distance is this, equation number 2. Okay, so we come back to our page and we write down our potential energy as V equal to mg y equal to mg h minus L cosine of theta. Okay, and this is our equation number 6. Now, as we know, the Lagrangian is, by definition, the Lagrangian is L equal T minus phi. That's the Lagrangian. Okay. Then we write down our Lagrangian as L equal to 1/2, equation number 5, right? Minus equation number 6, right? We have here 1/2 of the mass, L squared theta dot square plus 2 h dot L theta dot sine of theta plus h dot square minus mg h minus L cosine of theta. This is the Lagrangian, and we call it equation number 7. And let's highlight it. This is the Lagrangian of the system, of the pendulum. And this is the part A of the problem. Let's do the part B. Okay, as we know the definition of the Lagrangian equation, of the Lagrange equation, is derivative with respect to time of dl d theta dot minus dl d theta equals 0. Because we have the Lagrangian already, we are gonna calculate these terms, the derivatives, to find the equation of motion. Then we have, let's calculate the partial derivative of the Lagrangian with respect theta dot. So we calculate the partial derivative with respect to theta dot. So that we have theta dot on this part of the Lagrangian, on this part, and that's it. So that is going to be 1/2 of the mass to L squared theta dot, because we are derivating with respect to theta dot, plus 2h dot L sine of theta. We can simplify these two. Now we calculate the derivative with respect to the time of this expression. So let's do this. Derivative with respect to the time of dl the theta dot, and this is gonna be m. Okay, the derivative, because theta is a function of the time, we calculate theta to dots, right? We are derivating theta with respect to the time, plus, because h is a function of the time, we have to do the derivative on this part of the equation, right? And this is going to be the derivative of h with respect to the time of h dot L sine of theta, plus, now we are doing the product rule, right? Do you remember the product rule for derivatives? Yeah, that's what I'm doing. So this is going to be h dot, now I'm derivating sine of theta L, but derivative with respect to the time of sine of theta is theta dot cosine of theta. So do you remember, it's straightforward to remember that the derivative with respect to the time of AB is equal to derivative of A with respect to the time times B plus a derivative of B with respect to the time. That's what I did. So we have that expression right now. Okay. Now we come back and calculate the derivative with respect to the time of theta. Because this first part, yeah, we derive with respect to only the terms that have theta. For example, this term and this term, right? Those are the terms that I'm gonna derivate with respect to theta. So the first term is gonna be m. Okay, m h dot L theta dot cosine of theta. Derivative of sine of theta is cosine of theta. So this is going to be m h dot L theta dot cosine of theta. This is 0. The derivative with respect to theta of this one is 0. Of this one is 0. So the only term that I have remaining is this one in the middle. But this 2 cancels with this 2. So I have mass h L theta dot and sine of theta, but sine derivative of sine of theta is cosine of theta. So that's what I got here. Okay, now I go and calculate the derivative with respect to theta of this term. This is going to be minus, okay, h, the derivative with respect of theta of h is 0, 0 minus mg, and the derivative with respect to theta of cosine of theta is minus sine of theta. But I have a minus sign here, and minus is plus, so I still have this minus here, and I will have minus mgl sine of theta. And I have these 3 terms, and I can write down the equation of motion of the Lagrange equation as derivative with respect to the time of dl de theta dot minus dl de theta equals 0. And this is going to be this term minus this term. Okay? And I will have m L theta dot L theta 2 dots plus h 2 dots L sine of theta plus h dot L theta dot cosine of theta minus m h dot L theta dot cosine of theta minus m gl sine of theta. Okay, this is equal to 0. I will distribute this m into all those terms, so I will have m L theta 2 dots plus h 2 dots L sine of theta m plus m h dot L theta dot cosine of theta minus, okay, minus this term m h dot L theta dot cosine of theta, and minus with minus is plus mgl sine of theta equals 0. Okay, we have similar terms. The similar terms are this one and this one. Okay, then we have m. Okay, I will cancel the mass because it's similar on all the terms, and I will have L theta 2 dots plus h 2 dots L sine of theta plus GL sine of theta equals 0. And I will take factor common of this L sine of theta, and I can write it down like here, like this, and take it to the other side of the equation. L two dots is equal to minus L sine of theta H two dots plus G. Right? And I will have something like okay, I forgot something here. I forgot to write down this L. Sorry, this L is squared. Sorry, this one too is squared. This is square. Okay, I got it. This is a square. This is a square. So I can simplify the equation. I can cancel this square with this, and I will have theta two dots is equal to 1 dividing L, taking the L on this side and sending to the other side, right? Equal to G plus H two dots sine of theta. And this is the equation of a simple pendulum, right? With the gravity as of the acceleration as G plus H two dots. Remember that the equation of a pendulum is theta two dots is equal to, I forgot this minus sign here. Remember that the equation of a pendulum is theta two dots equal minus acceleration of the gravity, right? Dividing the length sine of theta, right? And this is our acceleration on this one. And this is the solution of this problem. Hopefully this helps you to understand some physics, and see you on the next video. Bye.